Hi guys, this is your video for the last part of lesson 26 about doing absolute mins and maxes. Absolute mins and maxes. And my writing thing is over here, so sorry if it gets weird that you're looking at the side of me. Just move me out of the way. Ooh, I can make myself smaller? I don't know. Okay. I'm already distracted. An absolute extrema. The highest point, the lowest point. An absolute max, an absolute min. They definitely exist for a graph as long as you have a closed interval. Okay. Whoops, I have not oriented this yet, so let's do that. It's just like we're in class together. I'm acting like I don't have my crap together. There we go. Okay. As long as we have a closed interval from A across AB, and as long as our function's continuous here, there's always a highest and lowest point. There's always a maximum, an absolute max, and an absolute min. That's the extreme value theorem, right? We always have an absolute min or max as long as we have a continuous function over a closed interval. So we're going to use what's called the closed interval, or excuse me, the closed interval method, or I like to call it the candidates test. And so this is what it looks like if they ask us to calculate an absolute max or an absolute min for a function within an interval. Step one. Amazingly enough, step one is calculate critical values. Critical values of f prime. So the critical values of f prime are going to give us options. There are possible relative mins and maxes. So relative or local mins and maxes can also be absolute mins and maxes. So given our f of x in this case is x cubed minus 3x squared plus 1. That means f prime is 3x squared minus 6x. When I set that equal to 0, to find my critical values, and I factor out 3x, I get a critical value when x equals 0 and a critical value when x equals 2. So these are potentials for relative max and mins. That also means they're potentials for absolute mins and maxes, or maxes and mins. But this is the part that gets completely different. When we do absolute mins and maxes, we need to compare y values. Y values from the original f of x function. This is not going to work by using the derivative. There's not a second derivative way to do this. The only way we can do an absolute min-max calculation is we find all the possibilities for where the absolute mins and maxes are, and then we do y calculations. So, why we call this the candidates test is we have candidates for our possible absolute min and max are. Our candidates are our endpoint x's, which is -1/2 and 4, and our critical value x's, which is 0 and 2. Now in this case, a table of information is going to be considered enough evidence of how we're going to answer the question. because I'm going to take each of my x's that are my candidates, and I am going to find the exact f of x that goes with it. And that is from the original function, the x cubed minus 3x squared plus 1. Now, some of these are easier than others, like a 0 plugged in. 0 cubed minus 3 times 0 squared plus 1 equals 1. Get me out of the way. All right. So, is that a min? Is that a max? Who knows? We'll know once we get some more values. The 2 cubed minus 3 times 2 squared plus 1. So 8 minus 12 plus 1, negative 3. So as of right now, min, max. Depends on what happens at 4 and negative 1/2 for us to get the rest of the story. Now you already might be looking and going, oh yeah, 4 is going to be more. Let's check this out. 4 cubed minus 3 times 4 squared plus 1. That's 64 minus 48 is like 26. No, 16 plus 1 is 17. All right. Oops, I don't want to circle that one. Undo. Oh. So 17, 1, 3. So 17 is now winning for max. Negative 3 is winning for min. We're going to have to see what happens with the negative 1/2. This is the one that's a little bit of a pain. So negative 1/2 cubed is negative 1/8 minus 3 times negative 1/2 squared is going to be negative 1/8 minus 3/4 plus 1. I'm going to come up here and finish that arithmetic. So negative 1/8 minus 6/8 plus 8/8 is 1/8. Not our min, not our max, neither. Now, the table is the proof, but we still have to be clear that to identify the values and where they are. So here's how I typically do it. Sometimes they ask us where it is, sometimes they ask us what it is, so I just give you both. I say my f of x function has an absolute max of 17 at x equals 4. F of x has an absolute minimum of negative 3 at x equals 2. Now, the important thing to remember is we are talking about a section of the function. We're not talking about the whole curve. We're talking about a section of the curve. That's why we can have always guarantee a min or a max on, if we're talking about the entire curve, it may not ever have a low or high point. It might continue infinitely in one or both directions. So let's pull this over here to be recorded. So this is our function, x cubed minus 3x squared plus 1. Remember, we are only looking at it on the closed interval from, I don't remember, something to 4, negative 1/2 to 4, right? Because negative 1/2 was the, so let's just, negative 0.5 to 4. Let me just zoom out. All right, so -1/2. Oh. Let me realign this. I'm going to try to mark some points on here. If you remember, the -1/2 x was the last one we did, was the y of 1/8. Oops, if you have a pen. Alright, so there's that point. There's the 0, 2, there's the 2, -3, and then up here somewhere is 417. So we're only looking at that much graph. So low, high. Turn, relative max, but not the absolute, because our interval went here. If we change the interval, absolute min and max can absolutely change. All right, I suggest at this point you stop the video and try the trick question. There's snag it and go ahead and pause. Try the trick question. And when you're ready, ooh, I can make myself big. Start the video again. And I'll do the trick question for you. Did you pause? You're supposed to be paused. All right, just a reminder, because if we're doing absolute maxes and relative maxes, absolute mins and maxes back in the original function, relative, we go into the derivative f prime, okay. And we also can use f double prime for absolute mins and max with the second derivative test attack. Okay, so this one's tricky. Sine squared x minus sine x. Trickiest part is the derivative. So if I rewrite sine squared of x using parentheses, then when I take my derivative, I'm going to have 2, let's do my derivative in a different color. Why? Because I'm just extra like that. Where's my eraser? Holy shit, holy Batman. I wonder if the cleaners, the custodians are going to break into my room here. 2 sine x cosine x. It's a little power rule, chain rule around the parentheses, minus cosine of x equals 0. That's the derivative set equal to 0 to get critical values. When I factor a cosine x out, I'll get 2 sine of x minus 1 equals 0. Now, if you were struggling and so you just went ahead and watched me start that, and now you're like, okay, let me see what I can, if I can try it from here, this would be a good place to pause. Make myself a little note here, sine squared x minus sine x. So, cosine of x equal to 0. However, what are my restrictions? What am I looking at? I'm not looking at the whole unit circle, am I? No. Up to the quadrant 3. All right, so where is the cosine equal to 0 in the first 3 quadrants? At pi over 2 and at 3 pi over 2, which is also an endpoint, so I'd have to test that anyway. 2 sine of x minus 1 equals 0, where sine of x equals a half. And from 0 to pi over 2, or excuse me, to 0 to 3 pi over 2, that happens at long x little y, pi over 6, and 5 pi over 6. So, when I test my candidates, I need to test 0 and 3 pi over 2, because those are the endpoints. And I also have to test pi over 2, pi over 6, and 5 pi over 6. Alright. I'm going to plug each of these into my original function. Whatever I plug in here for that sign, I have to then square that result. So the 0, 0 is the easy one. 3 pi over 2 is going to be a negative 1 squared minus negative 1. So it's going to come out to be a 2. Pi over 2 is going to be 1 squared minus 1, which is a 0. And it is possible with a trig function, since it's periodic, because cycles back and forth, we could have repeated absolute mins and maxes. Pi over 6 is going to be 1/2, right, sine of pi over 6 is 1/2. 1/2 squared minus a half. And 5 pi over 6 is going to be the exact same thing. So that's, in both cases, a fourth. Because 1/2 squared is 1/2 times 1/2. 1/4 minus 1/2 is negative 1/4. That's our min. So we've got mins there and a max there. So f of x, absolute max. So on the interval 0 to 3 pi over 2, f of x has an absolute max of 2 at x equals 3 pi over 2, and absolute mins of negative 1/4 at x equals pi over 6 and 5 pi over 6. Now, when we're doing something so concrete, meaning like there's an actual function that we can graph, that's a great option for us to do another Desmos check. Equals, we use some parentheses, sine of x, quantity squared minus sine of x. And this is also fun because we don't really know what this looks like. This is what sine x squared minus sine x looks like. It alternates big peak, little peak, big peak, little peak. 0 to 3 pi over 2. Well, 3 pi over 2 is like around, pi is 3-ish. So 3 times 3 is 9, divided by, it's like 4.5. So let's go this way a little bit. Okay, there we go. So here's 0. And you can see, yeah, there's our max, right, at 3 pi over 2. I wonder if I click this, if it'll get me a I wrote on it, so it might not. Oh, there it is. Hang on. Let me move out. Move out of the way, Mr. Purple Point. Look at me. Did you see where that purple point was? Yeah. And then look. Pi over 6. 5 pi over 6. Yes. All right. Okay, so hopefully that can help you work through some of the absolute min and max questions. We will do the graph question together in class because everybody needs some information on that. All right, hope you have a good weekend. Signing off.